And it's a pleasure to have Professor Vitor Cardoso from Centra in Portugal with us today. And he will be talking about illuminating darkness with gravitational waves. So I will now leave it to Professor Cardoso. So questions are mostly will be entertained at the end, but in between, when Professor Cardoso feels, he will give you some opportunity to ask questions, and then you can certainly ask questions. Otherwise, we'll take it at the end. So thank you very much, and I just invite Professor Cardoso to start this. Thank you.
Thank you, Sumanta. I'm very thankful to the organizers to invite me. It's a great opportunity. It's a great topic, and it's a wonderful and vibrant community. It's a pity that we're all going through this state of affairs, this pandemic worldwide. So I hope that I'm going to at least pass on a positive and optimistic note regarding science. So, there's a lot of science to be discussed, and I think we all want to understand the relevant questions that we should focus on, that we should spend effort on. There's many. I collected some of them in this slide. For example, how did the universe begin? How is the universe expanding? What formed black holes in the universe? How do black holes grow? Where exactly are they? How do they co-evolve with the host galaxies? How do they power, most of the cataclysmic events in the universe? What's the matter content of the universe? What exactly is dark matter? And perhaps the most pressing issue to understand is the limits of the general relativistic description of gravity. For example, how can we resolve singularities that are hidden from us by event horizons? Actually, how do we know that horizons are out there in the universe? So, do we know that cosmic censorship is upheld in all the dynamics that we know we can have in the universe or not? So these are some of the, I think, most relevant questions that we need to attack in the next decades. And of course, I'm here talking to you because we now have a tool, which is gravitational wave astronomy, to at least start thinking about these issues. And when you start going through the list, you will notice that there's a common ingredient to all or to almost all of these fundamental aspects, and that's gravity. Gravity is always playing a role in these aspects. So we need to understand gravity and gravity-related phenomena. Now, when you start thinking about gravity, then the basic building block seems to be a black hole. Okay, the simplest vacuum solution that GR, non-trivial, that GR has to offer us. And I'm going to remind you that in general relativity, black holes are really, really simple. Any regular and asymptotically flat solution of the vacuum field equations is described by this geometry over here. Okay, so this describes the Kerr family of black holes. It's parameterized, so I'm using units where Newton's constant and the speed of light are 1, but it's easy to plug them back in the line element. Okay, in these units, all you have in this vacuum solution are the mass m and a spin parameter a. Okay, and this solution describes a black hole, so it has an horizon in the spacetime as long as there's not too much angular momentum in the spacetime. So as long as this parameter a is smaller than m. Okay. And for those who've seen this in classes or who are used to working with this line element, it doesn't seem special at all. Okay, there's 2 parameters. But if you think about it, right, it's a very, very special solution indeed, because it describes any vacuum black hole in the universe. I mean, there's trillions of black holes out there. Any one of them, if we're talking about a sufficiently vacuum isolated black hole, is described by this solution. That's really amazing. Just think about the number of parameters that you need to use to describe yourself or the room you're in, right? So it's really special. And Chandrasekhar had this elegant formulation of this of this property, that in his entire scientific life, this was the most shattering experience, the realization that one exact solution of the field equations is an absolutely exact representation of an untold number of black holes in the universe. So this is one special property of black holes. I will also be using one other special property of black holes that's related to the possibility of extracting energy, okay? It's a simple experiment that you can do. You just track geodesics in the space-time of that spinning black hole. And you will find that there's a region there, which I'm going to call the ergo region, where objects within this ergo region cannot remain at rest with respect to a distant observer. For example, if I'm standing here looking at a faraway black hole, there's no object inside this region, okay? So inside, let me assume that the ergo region is inside this ring. No object here can remain at rest with respect to me. It could even be a spaceship with an immensely powerful engine. It's not able to remain at rest. Now, when Penrose realized this property, he also realized that there was a simple way to extract energy away from spinning black holes, right? So the idea, well, one idea at least, my interpretation of this is the following. You build a circular metal ring, so this ring over here, okay? And you attach it to a couple of shafts, and they are glued to a magnet, right? Okay, now the diameter of this metal ring was made to be small enough that it fits in the ergo region. So what I'm going to do now is I lower this metal cylinder, this metal ring to a spinning black hole where it's inside an ergo region. I just told you that nothing can remain at rest. So the cylinder, so this ring has to co-rotate with the black hole, right? But it's attached to a magnet. So the magnet has to spin, and now you just use Faraday's induction law, and it will tell you that this lamp over here has to light, right? So it's an amazing thought experiment that tells you you can light a lamp just using a spinning black hole, and this means, of course, you're extracting energy away from the black hole. Okay, and I will use this property later on. Now, of course, all of this was suddenly made more relevant because we have very strong evidence that black holes in our universe exist. This was the first example that we saw via gravitational waves. This, of course, is a simulation of a pair of solar-like black holes. They were spiraling very far away, emitting gravitational waves. These gravitational waves hit our detectors on Earth, made them vibrate, and we saw a signal. Of course, all of this, by the way, is obviously exaggerated many, many orders of magnitude. And when our detectors see this signal, we basically translate this signal into something that looks like this very popular figure, which tells you the relative displacement in these detector arms as a function of time. Okay, the y-axis is in some arbitrary units. I won't need them for now. Okay, the important thing is that the signal is what we need to focus on for the next decades and try to understand how much science and physics we can extract from it, right? Now, the relative displacement in our detector, this figure over here, is basically mimicking what the source is doing. And the source is basically a pair of massive black holes orbiting around each other. Gravitational waves tends to circularize the orbits, so these are on a quasi-circular orbit. They're losing energy via gravitational waves, so they need to come closer together. They need to in-spiral. But if you use Newton's law, you know, this system is quasi-Newtonian, at least initially. This also tells you that the frequency of this motion is increasing, right? So the system tends to acquire a higher velocity, and this means that the amplitude of the gravitational wave is growing in time, and the frequency is growing in time. So you see this beautiful signal, this beautiful chirp signal that basically stops, ends when these two objects merge, and they form what we think is a stationary Kerr black hole as the final merger product. Okay. So now we need to extract science from this. And traditionally, it's not the optimal solution, but it's the easiest way to think about this, is to try to divide the signal into kind of two stages. For example, I can roughly understand the signal when the system is non-relativistic, so the early stages of the in-spiral, when the black holes are separated, well. But I can also look at the final remnant, a final almost quasi-Kerr black hole, and try to understand what's going on. Okay. Now, focus first on the inspiraling stage. This was already discussed at length by KG Arun, but I'm going to go over it very briefly again. The idea is simple, right? You take the system, it's bound by the gravitational interaction. So a binding energy that goes like this. Mu is the reduced mass of the system, m is the total mass, L is the orbital separation. Okay? And it's losing energy via gravitational waves. So if you use the lowest order expression, this gives you the quadrupole formula, which is this term over here. Okay? Now, this energy loss, of course, you can use a quasi-adiabatic approximation. It's coming directly from the binding orbital energy. And this roughly tells you how the distance and frequency of your system is evolving. Okay? We usually express this as a phase psi for the gravitational wave, which depends on, of course, on the frequency, f. Okay? And the leading order, of course, you factorize this term over here, you would get a 1, this term over here, okay? But of course, we want to do more than just to confirm GR. So we need to assume that something else might be out there. For example, other interactions. If you have other interactions, the black holes could be charged, right? Then, of course, there's other terms for the binding energy, and there's other possible radiation channels. For example, dipolar emission of electromagnetic radiation. So one possible way to proceed is to ascribe unknown parameters to other terms in this post-Newtonian series for the gravitational wave phase. Okay? And it's common to see, to make a correspondence between these parameters and some physics. For example, this -4pn parameter is tied to the variation of Newton's constant in some models, okay? In some models, if G varies over time, then there's a -4pn term in the phasing. We know, it's an easy calculation that you can do in 5 minutes, that if there's electromagnetic charge in the objects, that's going to give you an extra -1pn term in the phasing. If the graviton has a mass, you get a +1pn term, and so on and so forth. Okay, so Kant also told you how tidal heating or tidal deformability affects the waveform at a higher pn order. So you see, we have a beautiful compact scheme that tells us how each physics is going to affect the phasing, and we can use observations to constrain these terms. This was done by the LIGO-Virgo collaboration. These are some constraints that were also discussed already. Okay, these are constraints on these coefficients alpha, if you wish. Okay. Now I'm just repeating the same slide. This is the gravitational wave phase. It depends on a number of parameters, and you can constrain each of them at a time. So you assume everything else is general relativity, vacuum, except one of these parameters, and you use observations to constrain them. And these are some of the constraints, for each of those terms and for some of the observations by the LIGO-Virgo collaboration. One thing that stands out from this plot, for example, is that it seems easier to constrain negative PN terms. And it's easier because they affect the signal at lower frequencies, right, where the system is spending a longer time. So it more or less gives you a more dramatic effect. So it's easier to constrain these parameters. But you see, this is a kind of a false sense of relief in some way, right? Because we don't know, we need to know what to expect. We need to know what to expect for these alphas. Maybe in, in modified theories of gravity, the magnitude of the -4 or the -1 PN is extremely small. So this actually doesn't mean much, right? We need to use physics in conjunction with this constraint. And there's a number of challenges. So I'm only basically going to discuss challenges in this talk, okay? There's a number of challenges that we need to keep in mind when reading results like this. For example, the constraints that LIGO-Virgo do assume that all of the other, except one Poisson-Tandem parameter, is equal to that of GR. But if you have any modified theory, almost any modified theory at all, okay, will affect all of them simultaneously, right? So, it's the translation from this sort of result over here to actual constraints on a physical theory is very non-trivial and sometimes cannot be done. As a simple example, if you take electromagnetic charge in your system, okay, it's going to affect the -1 PN term, but it's also going to affect the quadrupolar term, okay, and a bunch of others. And you don't want to be doing an analysis on a theory by theory case, especially because you don't have you don't have a large set of theories that you understand well, right? But the other challenge is that most of the correspondence between a PN parameter and the theory is done with a very, very hand-waving argument. I can tell you examples. For example, the massive graviton theory, the argument is entirely based, or was entirely based, on the dispersion of massive waves, right? The idea is that low-frequency waves are more heavily distorted, more heavily dispersed. They travel at a lower velocity, so the signal is distorted with respect to that of GR. But there's no first principle calculation of a waveform in a massive gravity theory, okay, period. And in fact, when you try to do that, you will find that there's other effects which are even more interesting. So we didn't do a first principle, fully fledged nonlinear waveform calculation in massive theory, but we can do perturbation theory. So we take a curved black hole and we fluctuate it in a massive gravity theory. The results are here. Okay, this is one example of the of a waveform from a particle, a neutron star, orbiting, in this case, a Schwarzschild black hole in a massive gravity theory. Okay, you do see dispersion. This is fine. Okay, and this actually, you see it right here. This is the waveform extracted at some arbitrary units at 10, at the radius of 10. This is the same waveform extracted at 100. And you see how the shape of the waveform is distorted after it travels. There's non-trivial dispersion here. But I'm showing you this because this is not even the most interesting aspect. The interesting aspect is that this entire signal is absent in GR. This is the monopolar component, so a spherically symmetric breathing mode. It doesn't exist in general relativity, okay? So you know, there's hard work, a lot of hard work to do to understand fully how to extract physics from gravitational waves. You can't just go around parameterize the hell out of waveforms and out of observations and blindly try to extrapolate to physics. And the same, by the way, applies to higher dimensional scenarios. It's very non-trivial to extract meaningful constraints on higher dimensions because you need a careful calculation of waveforms, and this has not been done. So there's a word of caution in this paper over here, but so far there's no first principle calculation of anything other than GR, basically. Okay. If you have questions, let me know now, because I'm going to focus now on the ringdown stage of black holes.
I have one small question. If you go back to the slide of the LIGO thing that you showed, -1 PN, 0 PN, 1. Yes. So here you mentioned 1 PN term is sort of a mass term for the graviton. But the figure shows that the constraint on the 1 PN term is very, I mean, it's pretty large, I mean, around of order unity. But we know that the mass of graviton has very high constraint from the binary neutron star data. So can you explain why this constraint is so small in this context?
That's perfect. That's a perfect question. This is precisely what I was saying, that, you know, reading this alpha one, for example, has G, has the graviton mass into it, and has the speed of light. It's a combination of these parameters. So even though the combination looks to be large, the constraint on the parameter you're looking for, it's still tight. It's, you know, it's 10 to the minus 22 or 23 electron volt. So it's constraints of the order of the separation, of the size of the separation of the binary. So you see, it doesn't look much here, but when you actually do the physics, which is translated to a specific theory, it happens, it so happens that the constraint on the mass of the graviton looks impressive, right?
Okay, yes, yes, I see. Thank you.
The same, so I'm going to show you similar results for lower PN numbers, yeah, and the same applies. Okay, so this is basically what I had to say about the in-spiral, but you can also think about the late time merger. So you think about the two colliding objects forming some highly distorted clump of matter that's then radiating everything it can until it relaxes to supposedly occur stationary state, right? And then ceases to radiate. So this stage over here. Now you see, if you go backwards in time, what you're seeing is a Kerr black hole that's slightly distorted. So it's vacuum GR slightly fluctuating away from Kerr. And this we understand very well. We know how to do linearized calculations of general relativity. And we know that the late time stage of basically any stationary state is a series of exponentially damped sinusoids. So the signal H, your gravitational wave, is a superposition of what we call quasi-normal modes. A signal which decays exponentially in time, so it's parameterized by this number omega I over here, but rings down as a consequence. But these are quasi-normal modes because, you know, black holes are intrinsically dissipative. Actually, stars as well. You're losing energy to infinity. If we're discussing a black hole, you're also losing energy to the horizon. So the signal has to die off eventually, okay? But the point is, we know these numbers very precisely. These numbers omega I and omega R, we know them very well. You can look at them here. There's routines to calculate them. There's data. We know them for decades, okay? So what we can do is perform something like black hole spectroscopy just by using gravitational wave observations. The idea is very similar to that which we do in acoustic physics or in the tuning of instruments, right? So for example, take a piano. Take a piano string. It's normal modes now. There's no dissipation, at least not that I'm not including any. Its characteristic frequencies are described by this simple formula. It's an integer times the velocity of propagation in the string over 2 times the length of the string, right? And any musician can, for example, detect the fundamental mode. If you detect the fundamental mode, you use this formula over here and you calculate the length of the string. If you're able to be a bit more precise, then then you can also detect the first overtone, so the first excited state, for which n is equals to 2, right? And you can repeat the calculation. You can also estimate the length of the string with n equals 2. And if they agree, it's fine. You have a beautiful string out there. If they don't agree, it means that either you have a large error in the measurement or it's not a string after all, right? And so the idea is exactly the same for black holes. With one mode, remember one mode now is a vibration and a decay time. With one mode, you measure mass and spin of the black hole, okay? With two modes, you test general relativity, okay? Now, the signal to noise ratio of LIGO observations is still not large enough to do proper tests of GR, but there's a clever way around this that the LIGO video collaboration found. So you can use the in-spiral stage to estimate the final mass and spin, so the mass and spin of the final black hole, and therefore the frequencies of the final object, okay? That's the solid line over here for the first GW150914 event that we saw, okay? These dashed lines over here are the Ringdown estimates. So we take, let me go back, we take the gravitational wave signal over here. We look for the Ringdown stage, so the phase where the signal is described by this, okay? So for that, we need to truncate the signal and forget everything that's before the merger, okay? And now, of course, this approximation is all the better the more you're closer to the final state, right? So what I'm showing you here is the parameters that you recover, decay time and frequency, when you start feeding a certain time after the black holes merge. So 1 millisecond after, 3 milliseconds, 5 milliseconds, and so on, okay? And what you see is, if you try to just use one mode to fit the entire Ringdown stage, it doesn't do so well if you use the entire signal 1 millisecond after merger, but it does very well for anything that comes after, okay? So it's not a fantastic test, but you know, it's just the first test. So it's an exciting thing that we're already doing. And this only uses the fundamental mode. You can show, there's a work by Baibov and Eisy and others that show that if you include higher overtones, even this outlier behaves well. So you're able to describe the entire post-merger phase with a series of exponentially damped sinusoids. Okay, these are one-mode tests that use the in-spiral stage, and they're already doing beautiful things. But you might be interested in actually testing your favorite theory, okay? So how do you do that using Ringdown? Well, the idea is simple. You need to do hard work. You always have to do hard work. Say, for example, you want to constrain, you want to admit the possibility that your black hole carries some charge, okay? So there's a theory over here that's been very popular for practitioners of dark matter theories. These are called milli-charged dark matter. There's an extra charge carrier, okay? But the theory otherwise looks like Einstein-Maxwell. So now the black hole solutions also have some charge in addition to spin, okay? So you know you have to calculate how the black hole solutions look like. We know it's Kerr-Newman. And now you need to understand how they ring down, okay? We also understand that rather well. So now you use, somebody's knocking on my door, sorry. No, I'm going to go for yeah. Sorry. So now you need to understand how they ring down. We understand that. you have not two parameters, mass and charge, mass and spin, you have three, okay? So you need to use at least two ring-down modes because that gives you 4 degrees of freedom, okay? But you can do it. So with ring-down, you can impose, if you have a sufficiently clear observation, you can impose a constraint on the charge to mass ratio, Q over M, to be smaller, roughly, smaller than 0.1 for a ring-down signal that carries a signal-to-noise ratio of 100. LIGO is far from seeing this, okay? But this will be trivial to get with LISA, okay? Now, the maximum charge to mass ratio of a black hole is 1. So it doesn't look like an impressive constraint, okay? But you can read this in another way. You can read this constraint as telling you that you're able to pinpoint 1 electron in 10 to the 19 neutrons. That's basically what this constraint is telling you, okay? And it looks a bit more impressive, they say. It's exactly the same, but it looks a bit more impressive, right? And so the game is always the same. You need to calculate the black hole solutions in your favorite theory. You need to calculate how these black holes vibrate, and that's it. Then you use observations to constrain it, okay? Now, you might worry that all that I'm going to discuss, all that has been discussed here actually in the morning and now, applies very well in vacuum. But our universe is a very dirty thing, okay? So how sure are we that cosmological constant, magnetic fields, accretion disks, dark matter, all of that is not going to affect these types of tests, okay? We did a very thorough study of this, of the impact of matter, of the real universe in these constraints, and they are summarized here, okay? So I'm giving you the correction to the ring-down frequencies that you get when there's matter, a lot of matter actually, close to the horizon of a black hole or close to the innermost stable circular orbit, or if there's some electric charge, some magnetic field, gas accretion, dark matter, and so on and so forth. This is the correction to the ringing frequency, so this delta R, and the correction to the time scale, this delta I. And you see that unless you do a dramatic change in your spacetime, unless you add a lot of matter very close to the horizon, the changes in the ring down frequencies are always smaller than 0.05% or so. This is way beyond our ability for the next decade. So we're fine. We can do tests of GR well, neglecting all the dirtiness that's out there. Okay, so we're fine over here. Actually, so I was discussing only ring down of isolated black holes. But actually, even binaries have characteristic modes. Okay, if you think about a single binary orbiting, so evolving via gravitational waves, this binary itself, in addition to releasing gravitational waves, also has its characteristic modes. Okay, it's an interesting thing. So I'm showing you, I'm not going to discuss this at all in any depth, but I'm showing you here the signal, the gravitational wave signal that you get from a binary when you perturb it, when you send some signal and you let the binary relax. It's not a single black hole anymore, it's a binary. And we always found a universal ring down signal also for the binary. This gives you the interesting prospect that you might excite resonantly the spectrum of a binary. Okay, we know it's almost impossible to excite resonantly the spectrum of single black holes. So maybe there's food for thought here. Maybe binaries are the object to look for if we're looking for resonant excitation. Okay. So before I move on to the ability to impose constraints on dark matter, I'm going to ask if there's 1 or 2 questions.
Yeah, please. Hi. My name is Partha Majumdar. We've met some time back. I wanted to ask you, when you say you perturb the binary, are these linear perturbations or do you go beyond? I mean,
These
really.
are linear perturbations. That's a very good question. So these are linear perturbations to a binary in the same sense that quasi-normal modes result from a linear perturbation of a single black hole. Of course, ideally, by the way, I would want to do a nonlinear fluctuation. So if you know how to do this, that's the way to go. But it's a very challenging, the problem with binaries is that they don't stick around to help you, right? They're evolving via gravitational waves. So you need to set up very carefully your problem to be able to study this. And you know, numerical relativity is still far from being able to give us hundreds or thousands of orbits, right? So for this study, for example, we had to construct a space-time which is a matching between two Schwarzschild black holes in a way that we're able to study the binary for long. Clearly, we need more sophisticated tools for this. Yeah.
Thank you. Thank you very much.
So
Very
can
well. Yeah, go ahead.
this is a very short question. So generally, the uniqueness, there are two theorems is mentioned in general relativity. One is the uniqueness theorem, other is the no-hair theorem. So when you do this kind of spectroscopy, which one actually we are testing? The uniqueness one or the no-hair one?
You know, the uniqueness and no hair are basically one and the same in general relativity, right? There's a set. So actually, that's a very good question. So thank you for raising this. As in any theorem, there's precise theorems of no hair, or if you wish, of uniqueness. We know that if you satisfy certain conditions, right, then the only black hole solutions are Kerr. Now, in GR, those solutions are either that you have vacuum, okay, or if you have a scalar field, which is a time-independent scalar field. So if you have a time-independent scalar field in space-time, the only stationary solution is Kerr. But my point is, there's conditions to be satisfied if you want the theorems to apply, right? We know of black holes which are not Kerr, which have scalar hair, so they don't satisfy the uniqueness properties. But of course, the reason is you break the assumption of the theorem. There's a scalar field, and it's a time-dependent scalar field. Okay, so I'm thankful for that question because it tells us that we actually we should do physics. We should use observations to test the predictions of the theory, and therefore to understand if the conditions of the theorem are satisfied, right? Yeah. And by the way, I should also say, I think I should echo Chandrasekhar's words. Our imagination is really, mankind's imagination is not very good, right? So we can think about some conditions, some theorems, but nature is a very vast thing. Let's just use observations and see how much we can squeeze out of them, right? And actually, that takes me to the next item, which is the elephant in the room. Can we use gravitational wave physics to understand dark matter? Now, there's different ways you can do this. Again, I'm going to use a compact binary in spiraling, but I'm just now going to surround it by some medium. This is my dark matter medium, okay? So here's my binary, and you see that if there's medium, the evolution of the binary, so the gravitational wave phase of your signal, is going to be different. Why? Well, the black holes are accreting some matter, okay? They also have to drag behind them all of the matter that's around them. This is called dynamical friction, okay? And so all of this, and I'm even neglecting the self-gravity of this distribution, okay? So all of this is going to result in a faster in spiral. Your binary wants to merge faster. It's getting heavier. It's dragging a lot of stuff behind, so it's going to fall faster, okay? And actually, we know how to calculate this when the wavelength of your dark matter is very small. So when dark matter looks like dust, very small grains of dark matter, we have it's not a good understanding. We have some understanding of how to calculate gravitational drag. Okay, so we know how it's going to impact on the phasing. It has an impact, well, a dominant impact at a minus 5.5 pn term. Okay, it's a usually negative term, so it's very low frequency effect. Okay, and if you use this naive impact on the gravitational wave phase, you can go back to observations and estimate how much is the environmental density around your binary. So I'm showing you this here in units of the density of water. It's arbitrary, of course, but I just like water. Okay. So I'm showing you the constraints that a detector can impose on the environmental density in units of density of water for different systems and for different detectors. For example, the event 170817, LIGO can use this to constrain the environmental density to be smaller than that of water. Okay, it's somewhere between 10 to minus 1, 10 to minus 2. Okay, but the longer, of course, the system stays in band, the better you're able to constrain, because this is a minus 5.5 pn term. Okay, so for example, ET, so future detectors, or LISA, can give you constraints which go down to 10 to minus 12 or even 10 to minus 16 that of water. And here, this gray area over here are typical dark matter densities. Okay, so it shows you that it's challenging, but if you have a good control of the physics and a good detector, eventually we're going to be doing dark matter physics with gravitational wave detectors. Okay, and this is just a mild dark matter model. Okay, there's a lot of things that I hid under this plot. In particular, all the ignorance that we have about what I'm calling gravitational drag. We do not know well how gravitational drag behaves when the binary is close together. Okay, so this is a brute extrapolation to regimes where LIGO or LISA would be seeing systems. It's maybe not a good extrapolation, but it's what we can do right now. So we need theoretical input on precisely this sort of calculation. This is for small Compton wavelength, but there's been a huge interest in large Compton wavelength. There are scenarios where practically all dark matter in the universe is basically just a very, very light scalar field. Okay, a theory that's well described by this action over here. It's a scalar field with some mass mu, which is very small. Compton wavelength is usually orders of kilometers, 10 to the 6 kilometers or higher. Okay. Certainly for this model, the previous formulas and description of drag do not work. Okay, so you need to redo this from scratch. Okay, I'm going to be talking about this. I know I'm going slowly, but I will discuss this a bit further. I'm showing you here that if you let go one of these scalar fields, I'm doing that in this plot over here. If you let go some initial distribution of scalar field, usually it settles down to what we call a boson star or an oscillaton. There's several names, okay? But these guys do form things that look like stars. And if mu is very small, it forms structures that seem like dark matter halos. It's very exciting, right? So if you use a boson mass of the order of 10 to minus 21 or 22 electron volt, this gives you structures which have the right dimension and mass for observations of the core of the galaxies. Okay, so it's an exciting prospect. So, well, we need to redo all of this, all of the calculations that allow you to calculate friction. Okay, this is something that Lorenzo Annulli and Rodrigo Vicente did. It's a painstaking work. Okay, the technical details are appearing in a couple of weeks, but let me summarize them very briefly. Okay, you need to evolve basically a theory where gravity is present, but you also have a scalar field and a binary, okay? You can show that this system, that you're able to reduce this system to two coupled equations, where for the scalar field, for the gravitational potential, and something that looks like a source term describing your binary, okay? For low frequency sources, you're able to calculate the flux of scalar field that this binary is releasing. And this tells you, this tells you the extra radiation channel that your system has to spiral inwards, okay? When you do the full calculation, you find something amusing, okay? And the something amusing is that this environmental scalar field, this form of dark matter, does leave an imprint on the gravitational wave phase, this delta upsilon. It's a -6 p.m. term, okay? It's even slightly smaller than the short Compton wavelength. So it looks like, I'm going back to my initial words, it looks like, oh, we're going to be able to provide immensely interesting constraints on this. But the coefficient of that term is here, okay? And for typical parameters, so a mass of 10 to -2 electron volt, and a frequency typical of LISA, 10 to -4 hertz, for example, you get a coefficient which looks like 10 to -24 relative to the dominant general relativity term, relative to 1. Okay, this term over here. So, in the next decade, if these are the parameters you're looking for, we are not going to be able to see this. Okay? But it's a calculation that you had to do to understand this. Of course, you might be lucky. Maybe dark matter has a much larger coupling. This mu is much larger than 10 to -2. Maybe the mass is larger than 10 to -22. But for typical parameters, the correction is just too small. But you need to do this. There's a lot of intellectual effort in modeling that we need to do, and that I urge all of us to think on. Okay, so this is dark matter as any dark matter physicist would call it, okay? Matter that you need to explain observations. But there are invisible sectors that gravitational waves can probe even better. You don't even need any environmental distribution of matter, okay? And give me 5 minutes to explain why, okay? So it's based on this ergo-region energy extraction mechanism that I told you, but now with waves. The idea is very simple. It was explained by Zaldovich. There's a thorough review here in this lecture notes that I did with my student and Paolo Pani. The idea is very simple, and it's simple to the tidal acceleration that Sukanta Bose already explained, but let me go through it again, okay? Look at this system, the Earth-Moon system. The Earth is generating tides, the Moon is generating tides on the Earth, but you see, the Moon is revolving very slowly around us. It has a period of roughly 28 days. On the other hand, the Earth is revolving underneath the oceans once a day, right? Very fast. So overall, this gives you two effects. The first is that there's friction, non-trivial friction between the Earth crust, this one, and the oceans, because you see the Earth is spinning under the oceans, the crust, okay? There's friction. So the Earth period has to increase, the rotation decreases. But the other important aspect is that there's a tidal angle. Because of this friction, there's a tidal angle between the tides and the Earth-Moon axis. Darwin called it tidal angle phi. It's a very small number, but it's non-zero, okay? Now you see the Earth is spinning, okay? And it's spinning down because of friction. So you might ask, well, where's the angular momentum going then? It can't just disappear because it's an isolated system, okay? Well, the angular momentum is being transferred to the Moon. So the Moon is getting farther away from us, and this has been measured, okay? Now, this system that we know so well is exactly the same as what Zeldovich described when he sent a wave towards any spinning object, for example, a black hole. You send a non-symmetric wave, a pulse of wave, to a spinning object, it's going to be amplified. It's going to extract energy in exactly the same way that the moon is extracting energy from the Earth, okay? This is called superradiance. And if the wave that you sent in is massive, okay, it's unable to travel to infinity. It's unable to escape. So it's bound to the black hole. It has to fall back at some point. But, you know, when it falls back, it's amplified again, right? So, you know, the only possible end state of this is an instability. So, in simple words, a massive field, a massive bosonic field, is unstable if it's evolving around the spinning black hole, okay? It has to extract the rotational energy away from the black hole. This looks like an irrelevant process, but if you calculate the time scales, the time scale is of order of 100 seconds for a massive scalar field whose mass is 10 to minus 16 electron volt around the 10 to the 6 solar mass black holes. These black holes exist out there. We've seen them, okay? And, you know, in astrophysical standards, this is nothing. The black hole is unstable just like that. So it's a very important instability, okay? Now, how does the instability develop? Well, you extract rotational energy away from the black hole. You have to deposit it somewhere. It's going to be deposited in the scalar field, okay? So at the end, you're going to get a structure that looks like a scalar cloud or a condensate co-rotating with your black hole, okay? And of course, you realize immediately that if this is a non-axis symmetric structure, it has to be releasing gravitational waves. Okay? So the estimate for LIGO was done a few years ago by Azimina, Arvanitaki, and their group. And they show that if a scalar field of a mass 10 to the minus 12 or 10 to the minus 11 electron volt exists, even with zero environmental amplitude, any small fluctuation is going to grow and is going to give you a gravitational signal. In fact, LIGO would see up to 10 to the 5 events, resolvable events, okay? And LISA would see up to 100 events just because there's a smaller number of supermassive black holes, but it's still impressive, okay? Now, you have to realize that if these fields do exist, we're looking for the invisible universe, okay? If these fields do exist, any black hole in the universe at some point in their lifetime would be unstable. So there should be a huge stochastic background of waves, okay? And in fact, so we did this study 3 years ago, and we showed that the stochastic background is so large that you can actually exclude, you're going to be able to exclude something like 10 orders of magnitude of field mass, okay? So for example, LISA would be able to exclude fields. The non-observation of this stochastic background would exclude fields that range from 10 to the minus 19 electron volt from LISA up to or down to 10 to the minus 11 electron volts with LIGO. So you see, you're constraining 10 orders of magnitude. You're doing particle physics with gravitational wave astronomy. It's really an impressive prospect, okay? That we should think about, we can do these constraints. In fact, you don't even need gravitational waves, right? Because if the idea is that your black hole is spinning down and transferring the energy to this cloud of bosons, then even electromagnetic observations are going to tell us something, right? So, for example, I'm plotting here what we call the Reggie plane, angular momentum versus mass, okay? The blue line is an instability window. Any black hole above this line, okay, would be unstable on timescales which are very short in astrophysical standards. Timescales shorter than 10,000 years, okay? If there would be a massive field of mass 10 to the minus 18 electron volt. Okay, but these crosses, so you see, if the time scales are so short, there should not be any black hole there if the field exists, right? So, but the observations show us black holes here. These are these red crosses, okay? So these observations already exclude a field with a mass of 10 to the minus 18 electron volt. It's fantastic. Actually, 10 to the minus 18 electron volt is the current best bound that CERN can do. We can do better. If you look at this yellow line is exactly the same thing, but for a massive vector of 10 to the minus 20 electron volt, okay? And if you trust astrophysicists, this black hole over here, Ferrel 9, is telling you that this field cannot exist because the black hole is spinning very fast, okay? Now, again, nothing comes easy, okay? There's a lot of physics we're neglecting when we do these calculations. We neglect coupling to matter, we neglect environmental effects, we neglect companions, and so on and so forth, okay? If you're dealing with gravitons, we know all of these are negligible. Gravitons don't couple to anything, basically, okay? And superradiant effects alone constrain the mass of the graviton to be smaller than 5 times 10 to the minus 23 electron volt. It's a bound that's now under review of particle physics. So we are doing particle physics with gravitational wave astronomy. It's really wonderful, okay? I'm not going to explain this. These are the current constraints from this effect only, superradiance, okay, on the mass of scalars, vectors, and tensors. There's a vast set of constraints. You can read all about them in these lecture notes. That, by the way, the original notes are from 2015, but there's a 2020 edition. It's updated on the archive a month ago, and it's going to be updated next year. So these are the constraints that we are doing with black holes right now. As I said, we are not including all of the physics here, okay? For example, we are not including tidal effects. But if you, so I'm showing you what can happen if you have a companion close to your spinning black hole where the cloud develops, okay? This is a simulation that Aishi Ikeda here did. And you see that now there's a plethora of phenomena. For example, your companion can start killing the instability by absorbing this cloud. It can even tidally disrupt the cloud. We've seen tidal disruptions happening, okay? But also, in some of these theories, where you have, for example, an axion or a scalar field, usually the theory was introduced to solve some problem, okay? For example, the QCD axion was introduced to solve the strong CP problem. So there's other couplings that you should consider. For example, couplings to the Maxwell sector, okay? And now you might worry that some of the energy that should have gone into the cloud is actually going to the vector field, is actually going to light, okay? So I'm showing you here what happens when you start tweaking the strength of this coupling, okay? K axion. This is a simulation for small K axion, okay? So this is going to show you the evolution of the vector field, so this Maxwell scalar F squared. And this over here is your scalar field that's in a cloud co-rotating with a black hole. Let me play this again. I throw a small electromagnetic wave into my system. My system is a spinning black hole with a scalar cloud around it, okay? I'm going to throw a small fluctuation, and that's it. Nothing happened. This is beautiful. We can trust all we knew with this coupling. But now I'm going to increase this coupling. I'm going to let my scalar speak easily with the vector sector, okay? So I throw again an electromagnetic wave, and now you see something is happening, you know? In fact, what you see is you get a parametric instability in the vector sector, and you get a huge release of photons from the system, okay? So you get a burst of electromagnetic radiation, you suppress the scalar in the cloud, Okay, and then the process restarts in you. So you're going to get periodic emission of electromagnetic radiation. We don't understand this system fully yet. There's a lot of things we need to understand to completely control this. So before I move on to my last topic, are there questions here?
Yes, please. Can I interrupt you for a second?
Sure.
You see, for superradiance, of course, the angular momentum of the black hole is actually carried away by whatever particles or fields you put in. And there's a concept of an irreducible mass. Hello, can you hear me?
I can hear, but there's some background. I think
Okay.
now it's fine.
Yeah. So what I was asking is, there's a concept of irreducible mass. So basically, the black hole itself spins slower and slower, and eventually it will not spin anymore. So will that act like a natural break? I mean, in the instability you talked about seem to imply
No. So that's a good one. That's a good one. So very good question. So what happens is the following. This is exactly like the Earth-Moon system, by the way. I didn't tell you this, but the reason. So when is this energy transfer going to stop? Well, it's going to stop when the angular velocity of the moon is exactly the same as the angular velocity of the Earth, because then there's no longer friction between the Earth and the oceans, the crust and the oceans, right? So this kind of process stops when the Earth always has the same face towards the moon. And actually, this is what happened in the moon, by the way. For us, it's exactly the same. Superradiance stops when the frequency of the rotational frequency of the black hole matches the rotational frequency of the field. But the rotational frequency of the field is only related to the mass parameter mu. So when you start evolving this process, what you find is that the black hole asymptotes to a fixed spin that depends on this mu over here. If mu is very small, then the spin goes to 0. Okay? And actually, you're just telling us how we could look for non-trivial fundamental fields. Because if a field of mu equals to 10 to the minus whatever, 11 electron volt, it does exist, then if I plot the regiplane spin versus mass of all the black holes I know, there should be a non-trivial cluster close to this value. Okay?
Exactly. You're absolutely right. So I was wondering if there's something like a quasi-normal mode from the cloud, as it happens. I mean, is that...
There is okay, yes, that's a more technical question. There is a quasi-normal from the cloud, from the black hole cloud system. So I don't know if it's properly calculated, okay? Because again, taking back reaction into account is very tough here. It's been done by a couple of groups using numerical relativity. It's non-trivial to calculate fluctuations of this system. Does this answer your question?
Thanks a lot, Vitor.
Yeah, can I ask a question about one of your slides? Going back to a couple of slides back, you had a slide where you had the time scale for you showed us this slide. So I'm surprised that this time scale does not include the spin of the black hole, because should you not expect the spin of the black hole to be in it?
Yes. Good. It should include the spin of the black hole. This time scale assumes that the mass is much smaller than 1 over the spin. Okay. There are corrections, of course. There are corrections that should be here that include the spin, because of course there is no instability if the mass is much larger than the spin. Okay.
Yeah.
So
thanks.
This equation is only a small mu expansion. Good, thank you.
Okay, thanks.
Hi, Vitor. This is Sukant. If I can ask a quick question.
Sure.
This description is really wonderful. The question is, for the, suppose you have a cloud of ultralight bosons. You mentioned there are ways in which one can constrain the mass of the boson. But how do you do that when perhaps you're also battling with other parameters, one of which you mentioned, like the coupling strength, but also perhaps the amplitude of the field? Are there other confounding parameters, and how do you square off on them to finally pin down the?
So that's wonderful. So there's one, I would say, fantastic aspect of this phenomena when there are no, so if we neglect couplings to other fields, so it's just a scalar field that gravitates and that's it. The wonderful aspect is that the amplitude of this cloud only depends on the initial spin of the black hole and on the mass of your field. And we know how to calculate that, okay? So we basically, it's basically a very solid, a robust emitter of gravitational waves. The total mass in this scalar cloud is usually of the order of 10%, 5, 10, 20% of the black hole mass. So it's a huge amount of mass in this cloud. And it's basically the only input we need to calculate gravitational wave emission, okay? And the other aspect is, these are, you know, it's a very slow evolution. So for all purposes, and I think all searches so far assume a monochromatic emitter. It's really just a monochromatic emitter of gravitational waves. And these are all the constraints that you see here are basically assuming, constant frequency emitter, or in the case of Cygnus X1, you're just looking for a spin down of your system in real time. So of course, there's a very narrow band where you'd see the system spinning down, so you don't need gravitational waves. But what I'm trying to say is it's a very robust mechanism that doesn't need a lot of assumptions. It's a different aspect when you're dealing with a full theory. So for example, this is the theory to solve the strong CP problem, an axion theory, okay? In this case, we do not know, I mean, we can speculate probably, but all those bounds do not apply to this. I don't think anyone knows yet what are the bounds on K axion or on mu if you consider the full theory. And this is one example. I mean, I didn't even include couplings to fermions, for example.
Thank you, Vitor.
Yeah. So that's an important question, which is there's a lot of theoretical input of hard calculations that need to go into this still. But I mean, my point is, I think it's an exciting time to be thinking about these issues because we have, and we'll have data. Yeah. Okay, so I'm going to move on to my final item, and this is, discussion of actual black holes. So I've been discussing how to use black holes to constrain new physics. I would like now to discuss the evidence for black holes themselves. And if you try to raise this issue, actually I advise you to try to raise this issue because there's a long and noble community of physicists that will tell you, we shouldn't be doing that. The only outcome of gravitational collapse of massive stars are black holes, okay? So you shouldn't be thinking about it. But on the other hand, physics is about observations. So, you need to know, you need to be able to tell with certainty how to quantify the evidence that the black holes that you're seeing out there emerging that the objects that you're seeing out there emerging are black holes. And there are theoretical aspects that actually force this question upon you. We do not know fully and satisfactorily how quantum fields behave. We do not know how to evolve in a satisfactory way Hawking evaporation of black holes. We don't know well the final state. We know at some point the entire semi-classical formalism breaks down. But even at the classical level, we have strong theorems that tell us that horizons are cloaking singularities, where the theory breaks down there. We don't even know if this breakdown of GR at the singularity is going to percolate to the exterior. We don't know because we don't have a theory for that. Okay, so I think it's very relevant, it's very important, and can be done. We can try to think about how to quantify the evidence that we are seeing black holes, okay? Now, before I move on, it's important to stress that black holes are black, okay? Black holes are defined by horizons. Horizons, you know, their own definition tell you that you would need to be eternal to verify their existence, okay? So let me just go quickly through the anatomy of an equatorial slice of a black hole because it will play a role here. Now, I think some of you may have done the calculation, and if you do the calculation of geodesics, circular geodesics in a standard Schwarzschild or Kerr spacetime, you're going to find that at large distances away from your black hole, so in this gray area over here, you're always finding stable circular motion. Of course, because you need to recover Newtonian physics. But curved spacetime starts showing up close to the central singularity, right? There is a point, this right region over here, okay? The boundary is the ISCO, the innermost stable circular orbit, where you cannot find stable motion, stable circular motion for time-like particles. If you go further in, you will find one extra special point, and that's the light ring over here. Okay, this circle over here is the only location in the black hole spacetime, well, in the Schwarzschild spacetime, where you can throw a photon and make it orbit on a closed trajectory. Okay, so if you think that a photon actually from a geodesic perspective is just a high frequency null particle, you can also understand that high frequency gravitational waves should also get trapped in this location. This is 3m for Schwarzschild, okay? It's unstable, right? So as time goes by, this photon or this gravitational wave should decay, either falling to the horizon or decaying to infinity, okay? And the important thing is observations of the late time relaxation of black holes, what I call quasi-normal modes, are actually observations of this stage, of this light ring, mostly, okay, mostly, of this region over here. They are not observations of horizons. They cannot be, because you need an infinite amount of time to observe phenomena closer and closer to the horizon, okay? So of course, challenges are huge if you want to actually discuss alternatives to black holes. You need to tell me which alternatives you have. You know, if it's not a black hole, what exactly is it? You need to tell me that they do form dynamically. We have seen black holes in all simulations we have. They are the natural outcome of collapse. They are the natural outcome of collisions. So if you're going to argue that you can form graviton stars, boson stars, fuzzballs, you need to show that they form dynamically and that they are stable. And then you need to show that if they exist, they look like black holes. And all of this is highly non-trivial. It will take decades, I think, to understand each of these items, okay? Let me show you at least some of the challenges, even at the stability level, okay? If you try, so we have seen objects that are very compact, and vacuum GR predicts that they have ergo regions, okay? Now, let me show you what happens if you produce an ergo region in a space-time that has no horizon, okay? Let's assume instead of an horizon, I place a mirror, some surface over there, okay? So I throw away, so my ergo region is this green region over here. This is spatial infinity, okay? And this is the object surface where I place the mirror, okay? So if you can think about this as the ergo region of Kerr, but now there's no horizon. There's something over here. I'm going to throw a gravitational wave at this spacetime and see what happens, okay? There you go. Now, if you remember, an ergo region is a region where negative energy states appear, right? Now, this wave penetrates the ergo region. It has a negative energy. But in the exterior, only positive energy states are allowed, right? So you see, energy conservation tells you that if there's a positive energy state here, then the negative energy state inside has to grow in amplitude. What this tells you is that spacetimes without horizons but with ergo regions must be linearly unstable. This was shown rigorously by Friedman and by Moschidis more recently, okay? So the first challenge is, if you want to tell me that horizons don't exist, you need to explain how these guys appear, because they are unstable, okay? But even if there's no spin, I'm going to skip this. Even if there's no spin, if you try to squeeze too much matter in a very small region, okay, at some point your star is going to be within its own photon sphere, its own light ring. So the surface is going to be within the light ring, okay? And there's an interesting result by Joe Kerr a few years ago that says the following. I mean, it's a mathematical result, so let me read it for you. If you kick a star whose surface lies within the photon sphere, then this kick is not going to decay faster than 1 over log of t squared. Okay, so in practice, if you kick the star, the fluctuation is going to stay there for a very long time. And the conjecture is that it stays there for so long that non-linearities take over and give you an instability. Okay? So these are two, I think, formidable obstacles against having horizonless objects. Okay? However, I usually point out that even though I love myself, I am also unstable. Okay? But my instability timescale is of order of, I hope, 100 years, right? I will die eventually. So it doesn't mean, I'm not important right now. So this to tell you that we need to understand timescales for this instability, and we don't have any control on that yet. Okay. So there's a long-term project here, which is to understand precisely the ergo region instability and the nonlinear instability of objects with photon spheres. And there's a lot of calculations that need to be put into this. So, but let me assume that all of these obstacles were solved. We have objects that look like black holes, yet have no horizons, okay? And now let me ask the question, do they look like black holes or not? I mean, or am I going to look out there and say, oh, no, surely that's not a black hole because it's luminous. Is this going to happen or not? Now, there's different ways of doing this. Again, either you use the in-spiral stage or you use the ring-down stage. And the nature of the objects in the in-spiral stage was already discussed by Sukanta and Arun, even in the way you parameterize the waveform. And of course, it's related to the way that vacuum black holes in GR behave. They're very special, right? Sukanta was telling you about the non-trivial tidal heating, the shear on the horizon that black holes in GR suffer, but they also have a curious property. When you take a companion black hole close to another black hole, in GR, the tidal deformability that it causes is 0. I mean, the horizon deforms, but the gravitational distortion that this guy causes on the companion is 0, at least if they are non-spinning, okay? Now, if you replace these two black holes by some non-trivial clump of matter, both these properties are going to change, right? So you're going to change the tidal heating properties of the object and the tidal deformability of this object. And of course, this is going to have an impact on the gravitational phase, which is what we see. I usually call this precision physics because you need to monitor very precisely the phase of the gravitational wave. But you can do it, right? But you can also, instead of doing precision physics, you can try brute force. You should ask for clear signatures. And one clear signature is going to should appear at the level of the final object, okay? You see, if the final object is not a black hole, but has some surface, the ring-down state should change completely. And the reason is very simple. Let me show you again why this ring-down that LIGO saw appears. I'm showing you here the gravitational wave signal in this plot over here as a function of time when a star, this red dot, is thrown into a black hole. Okay. This orange line is the light ring of the black hole. Okay. Forget about the black dot; it doesn't mean anything. It was just a marker. Okay. And you see that the gravitational wave signal has a burst when the red dot crosses the orange line. So there's a burst of radiation when your object crosses the light ring. Okay, most of the radiation that LIGO sees, this burst, is actually produced when the objects cross, let's say, a common photon sphere, a common light ring. There's no relation to horizons. Forget about horizons. We cannot see horizons, okay? Right? But then you see, you're exciting the light ring, the photon sphere of the black hole, and this excited photon sphere radiates. Some radiation is traveling outwards. It goes to LIGO. LIGO sees that radiation. It's here. Another fraction, it's traveling down the horizon. It's traveling downwards. And you never see it again, okay? But now, try to make the horizon disappear. Try to place some surface here. What are you going to see? Well, the fraction of the energy that was traveling inwards has to interact with the surface, and then at some point it has to exit, okay? So you're going to have a non-trivial final stage. I mean, this is very curious, right? So I'm showing you here again in the static plot what you should get. So this is the black hole case. This is the effective potential that gravitational waves actually see. Okay, the potential that they need to cross is non-trivial. It's peaked at the light ring, roughly. Okay, and then the waves see nothing. The potential is trivial. They travel to the horizon if it's a black hole. Okay. Now, on the other hand, if you, for example, if you study a wormhole, if you just glue two of these black holes together and you travel to another universe, you know, roughly, it's just a glue and paste technique, you're going to see another light ring at the other end. So the waves now, they cross this, you excite the light ring, some come to LIGO, some try to travel to the other universe, but they're stuck. They see another light ring, so they come back, a fraction has to travel again to LIGO. So you're going to see echoes of the original signal, okay? But suppose you're more conservative. You don't want wormholes, okay? You just have something that looks like a star, okay? Well, the same thing happens. You excite the light ring, it's this blue line over here, the potential that gravitational waves see. You excite them here, okay? A fraction goes to LIGO, a fraction goes inwards, but now at some point it interacts with the surface of your star or even the origin. It needs to travel backwards. So again, you're going to get non-trivial echoes in your gravitational wave signal. And now we're not talking about precision physics because there's a substantial amount of radiation that can come under the form of echoes, okay? Echoes, these are echoes because you have a cavity here. So it's echoes in the same way that my voice is echoing in this room that I'm in, okay? So these are somewhat, let's say, classical consequences of not having a horizon. But we have recently realized that there's other ways where you can get echoes and they are almost orthogonal, okay? So this is a surprise of trying to think about consequences of quantization of black holes, okay? And one of the original proposals by Bekenstein and others argued that the area of black holes comes in integer numbers. This is like the Planck quantum, right? And of course, this quantum of area should have something like the square of the Planck length there. It seems a negligible effect, okay? A real classical black hole is just a huge number of these quanta, okay? But now try to see what happens when you send a gravitational wave into one of these macroscopic objects. Well, you're going to change the quantum numbers by some fraction delta n. There's a non-trivial delta n, so this is the number of quanta in being excited, right? And this gives rise to a non-trivial area change, okay? This translates, of course, we know how to translate area and mass for a classical object. So this translates via the quantum of energy, h omega, into a non-trivial frequency. And you would think that this quantum of frequency are at the Planck scale, but they are not. It's a funny consequence, I think, of holography, probably, that if you do this calculation, it's a one-liner. The calculation tells you that these quantized frequencies are actually in the LIGO range. I mean, just evaluate this number for n equals one quantum jump, okay? So it's a classical thing that LIGO seems to have access to, okay? So this tells you that if this number alpha, which we do not know, is of order 1, and if Bekenstein's idea is correct, then LIGO should start seeing consequences. And the consequences are several. The first is, you know, if the Ringdown actually is probing the quantum regime, some of these frequencies, some of the Ringdown frequencies of black holes, which are produced in the photon sphere, should not be absorbed. But you know what happens. Now we know what happens when, you know, when a wave is not absorbed by a black hole. You should start seeing echoes, right? So the consequences of a non-trivial quantization condition on these objects are first, again, echoes from an entirely different scenario, but also a different tidal heating. And this is even more elegant because tidal heating and tidal deformability are effects that happen at lower frequencies, right? So you have a better prospect of probing quantum phenomena because quantum transitions are suppressed. So you're going to suppress tidal deformabilities and you're going to suppress tidal heating for quantum black holes. And we can study that through precision gravitational physics. And I've talked too much, so I'm going to finish by saying that we are entering really a fascinating new era in science. We know we have gravitational wave astronomy. It is becoming a precision discipline. And we can test some of the outstanding decades-old problems, issues in physics. What is dark matter? How exactly are we going to resolve singularities in black hole spacetimes? And do black hole spacetimes behave as Einstein says they should? Okay, so there's a lot of excitement. I'm very happy to be here discussing this with you. Thank you.
Thank you very much, Professor Cardoso, for such a nice talk. So it's now open to questions. So may I request the attendees if they have any questions they can ask Professor Cardoso.
May I ask a question or two questions, please?
Professor, before that, there were a few questions in the chat. Let me just repeat it.
Sure.
Then, yeah. So one question was from. Yes. So it's from one question is that the way I understand this is regarding the superradiance, that the test that you mentioned can only tell us about the mass of the field. And he's asking, can this test tell us more about the nature of the field as well? So do you have any comment to that?
So that's true. So the bounds that we impose on the field are only related to the mass when we neglect the other couplings and we assume a nature for the field. It's a very interesting question. I am not sure what can be done to infer the nature. For example, inferring the nature, I'm thinking about, can we tell if it's a vector or a scalar?
Yes.
I do not know. I'm sure we can. It will require a lot because the details of the instability depend sensitively on the spin of your field. A vector field is strongly more unstable, so unstable on shorter timescales. So if we have a sufficient number of observations, we will be able to understand the nature, in this regard, the spin of the field. But I do not have a clear answer how to do that test.
The other question is from Abhishek Hegde, and he asked that do we check if the theory is well posed before calculating the waveform in alternative theories?
Wonderful question. We do not know. So actually, that should have been my first challenge. So for these theories that I discussed in Superradiance, massive, minimally coupled massive scalars or vectors, the theory is well posed. In some sense, it's a trivial extension of GR, right? I mean, you just add some non-trivial matter content, but that's well posed. But for all the others, including massive gravity, you know, we don't know. Massive gravity, dilaton, Einstein-dilaton Gauss-Bonnet, Chern-Simons, almost any theory you can think of, we do not have a proof of well-posedness, and we don't even know how to do that right now. So again, this goes to, in fact, this goes more to my initial point, which is we can't just read blindly physics consequences from constraints on PN parameters or Ringdown and so on. There's a lot of effort that needs to be directed towards understanding the fundamentals of the theory.
Then there is one more question which says that what does it mean to say black holes are inherently dissipative?
Oh, it just means that inherently means that first the condition, so I'm speaking about isolated black holes. When you're fluctuating a black hole, the gravitational wave has all of the space-time available to travel. This means that there's dissipation at spatial infinity. You lose waves because they travel to spatial infinity, but you also can lose energy traveling down the hole. And in fact, for the type of black holes you work with, eternal horizons, you know, the usual boundary condition is a no outgoing boundary condition at the horizon. So you have dissipation at the horizon itself as well.
Okay. So I think these are all the questions I could see in the chat box. So Professor Majumdar, you can go ahead with the question.
Thank you. Yeah. Well, the first question was about some work which I saw last year, which implied that if you have these exotic compact objects without a horizon, then if they do accrete matter, there is some argument based on the hoop conjecture of Thorne that these objects may eventually get into their Schwarzschild radius and become black holes. So there's an instability that this work, I forget who the author was, is trying to claim that even though you may have in spiraling binaries made up of these exotic compact objects, eventually, or even if the merger remnant is an exotic compact object, but if they do accrete, then they would become black holes in the long run. I mean, at some time scale, okay?
Yeah, so actually those were two works, one by Jan Bei Chen and students at Caltech, and I think the other by Nico Yunes and others. So it's in principle an elegant constraint, but there are strong assumptions. There are strong assumptions regarding the equation of state of this horizonless object, right? The idea is very simple. They use the Hooke conjecture to state that if you accrete a sufficient amount of matter, because horizons usually grow superluminal, at some point the horizon is going to eat the object. But there's a strong assumption regarding the heat capacity, if you wish, of your exotic object. Okay. So in general, you can easily evade this constraint if you're clever enough in constructing the matter that you put in the object. But actually, thank you for raising this issue, because there's another constraint, a very let's say popular constraint on this type of objects, they were done via the non-observations of tidal disruption events. The idea was simple, right? If you have a compact object that does not have an horizon, I throw, for example, a star at this guy, then, if there's a surface there, I should see a flare, right? Or if I have accretion, like Sagittarius A, then accretion should at some point be in thermal equilibrium with the central object, and I should see also a right spot.
Right.
And the original constraints are ridiculous. They constrain this epsilon parameter, so how far away the surface is, to numbers that are 10 to minus 35 from the non-observation of a luminous spot on Sagittarius A. Now, unfortunately, again, there's a number of assumptions that go into this. And one of them is just interesting physics of GR. And it's in this drawing. I mean, we put it in this Nature Astronomy paper. I think Abramovich also discussed this. Electromagnetic waves and gravitational waves are strongly lensed in compact objects. What this means is, if you try to shoot a photon out of an object that's very, very compact, you're going to have a hard time making the photon escape and be seen at infinity. The trajectories are here, right? It's quickly going to fall back onto the object. And the point is that it's very, very hard to achieve thermal equilibrium between an accreting, very compact object and accretion disks. So these bounds need to be strongly relaxed. They have been, in the meanwhile, relaxed. This paper gives some updates, and the tidal disruption events as well. Okay? So there are still interesting constraints from these observations. They need to be relaxed. And again, I think we all, as a community, need to go back and see what exactly are the assumptions and how exactly are we going to improve on them. But yeah, so again, that's a clever way of constraining them. There are assumptions behind it.
I think.
Okay, so I just have one more comment and I'll be done. I'm taking a lot of your time.
Maybe, Professor Partha, maybe we do another seminar after this, and maybe the others may have also some questions. So we have a discussion session tomorrow at around, it's in the schedule. Maybe at that time we can all discuss all these things. So I will ask if any other person have another question, please to ask.
Hi, I have a question.
Yes.
Hi. Yeah. So this is related to the superradiant instability that you were talking about. So last year, your work with Paolo Pani, you showed that if you have any kind of absorption, a very small absorption at the horizon, so the instability is curved. So from my understanding, the instability essentially arises if you impose some kind of a dirichlet boundary condition at the horizon, or if the horizon is completely reflecting everything that you throw at it. But for any like exotic compact object, like which is modeled based on some kind of quantum physics, or let's say the model that you are showing as well. So there you don't have infinite potential at the horizon, right? So you would have some kind of finite potential. So why do you still worry about the instability? Or rather, my question is there...
Oh, no. So that's a good one. So this instability is always there. So if you're talking about this is just a centrifugal barrier. I mean, this exists for any object which is regular. I mean, at the origin. This is a Newtonian physics thing, right?
Okay, so it doesn't...
You need to reflect, the wave travels to the origin, it needs to come back, right? That's it. That's just that.
Okay.
Okay, but now you raise an interesting question. So I don't have it here, but there, in our work, we show that any object with spin without horizon is unstable. This was also a theorem. It's been verified numerically. If you add by hand, this is important, in the boundary condition, some sort of dissipation, you can kill the instability. What has not been shown, and I think it's an interesting open question that if you can, you should look into it, is if these boundary conditions actually arise naturally for dissipative matter. We can talk more about this, but well, I am not sure that if those boundary conditions arise naturally when you have a reasonable object made of reasonable material.
Okay, thank you.
Yeah. So I think we do need to worry about instability.
Yes, I guess we can take one last question in this session. Anyone?
One question.
Hello? Anyone has any question?
I have a small question to Vitor.
Okay, sure.
So this is regarding probing the quantum structure of black hole via this echo and your recent results. So
Right.
I was wondering that given the black hole mechanics and laws of black hole thermodynamics, whatever, so what should we expect that via this kind of approach, be able to probe the departure from those assumptions underlying those laws, or some kind of also some kind of extra factors from the Bekenstein-Hawking law corrections, or should only the fundamental fundamental
Good. I see where you're going. I think you can. So right now, the only thing we have been doing is assuming that there's a classical correspondence, right? And so we're using classical vacuum general relativity formulas to test, well, not to test, to understand what we could expect from the quantum version of these laws. But I am sure that something similar will happen if you have, for example, corrections to the entropy formula. Right? Which probably is what you're hinting at. So I'm sure that if you add corrections to the entropy formula and go back to their quantum versions, you're also going to have imprints. I am not sure how well we can test that. Yeah.
And, just a comment, I mean, this delta A term has only mass term, but for a rotating black hole, in principle.
Oh, yeah. We do, yeah. So in this work, we do include spin. This was only to show how a kilohertz frequency can arise out of what looks like a quantum argument.
Okay, thanks.
Thank you very much.